Assalamu alaikum. Alright, so today what we're going to talk about is basically chemical equations. Now, the thing with chemical equations is that they basically represent the way chemi- chemi- chemical equations represent the way chemists really communicate with each other. We have already studied the words for it. We have studied the chemical formula. We know that formula tells us so much more about a compound than a simple common name could. Like H2O tells me so much more about water, its composition, its properties, the kind of bonding it has, the MR that it has. I can figure out so much by just knowing H2O instead of knowing water, right? So unless you've experienced what water is like, you will be at a loss when I said what water is. But if you know chemistry, then H2O tells you so much more that even if you haven't experienced that thing or haven't worked with that thing, you can pretty much predict a lot of things about that thing and guess a lot of things about that thing. So that power of inference comes from having good notation, having good grasp of knowledge and the concepts in chemistry, and of course it comes from having a good communication system, just like chemical formulas. So today we will be focusing on chemical equations, which are like, if chemical formula is words to the conversation, then chemical equations is the whole sentence. And it's not just a sentence. Every chemical formula is basically a story. It's a story of every chemical equation. It's a story of how things start. What do you start with and what you end up with, and what happens, what changes go through, what changes happen to those particles when they make these chemical processes happen. And of course, it is always so exciting to build new things, and chemical equation is always a story of something being built from something else. Now, chemical equation, of course, it starts by understanding the basic structure. Now, the chemical equation, as you already know, starts with a reactant. So on the left side, we have reactants. These are the things that start the reaction. And there's an arrow. This arrow is telling me that the chemical process has started from the left side and is ending towards the right side. And this is my product. Now, of course, there is so much more going on to any chemical process than just reactants changing to product. It doesn't happen like that. But all of that thing, like how does it work, that we see in what we call mechanism. So this is just reactants going to products. It's telling me what the equation is, what the process is. So I'll take a simple example. I want to make water by burning hydrogen. So I take hydrogen and oxygen to make water. Now this same thing that I just wrote in English, I can write it down, I can translate it to the idea of chemistry, that hydrogen and changes to plus oxygen makes water. So I've written it in the formulas. Now, what's important over here is knowing the law of conservation of mass. Now, basically, there are four things that are conserved. The idea of conservation is that whatever you start with is what you end up with. You cannot create that thing. So whatever you start with, for example, mass, whatever you begin with, whatever mass you have is what you're going to end up with. So mass, charge, momentum, and energy. These are the four things that are conserved in our space. These are the four things that are conserved in our universe, which means that whatever you start with in the beginning of any process is what you're going to end up with. So energy does not change, does not increase or decrease in amount in any chemical process. But what happens is that its amount may change, its form may change from one form to another. It may go from heat to sound, or being stored in bonds to being released into the atmosphere. So all of those things can happen, but will never be created or destroyed. And same is the case with momentum, charge, or mass, which means that whatever happens over here on the left side, whatever mass I have on the left side is exactly the mass I should have on the right side. And of course, that is not happening here. Right now, this equation is violating a very basic tenet of modern chemistry and physics, that whatever atoms you start with are the atoms you end up with. So for example, on the left side, if you notice, I have two hydrogen atoms joined together, of course, in a hydrogen molecule, but there's two oxygen atoms as well joined together in oxygen molecule. Hello Ali, good to see you here. Now those two things are joining together and making water, but in one water molecule you have two hydrogen atoms and one oxygen atom. So clearly one oxygen is not being shown here, and that can't happen. Mass of that oxygen, where did it go? It has to be accounted for, and for that reason we do what we call balancing equations. So how do you balance? Now I have come up with a few methods or techniques over the years. You probably won't find them in any book, and this is more like a guesswork. An algorithm might exist for this, but I usually try to work with a few techniques that I'm going to share with you today. For example, whenever you're balancing an equation, first I would suggest that try to understand what you're working with. Are you working with atoms or are you working with ions? So if you're working with ions, then balance ions, and if you're working with atoms, balance atoms. So that's the first thing I would suggest, that balance the particles you're working with. So what that means is that you have ions or atoms. So it is your choice to work between atoms or ions. Second factor that I would suggest is that do oxygen at the very end. So keep oxygen for the last, keep hydrogen for second last, and balance everything else before that. So the order goes like this. So any other element or any particle, then hydrogen, then oxygen. Of course, sometimes we have to come back, and that's perfectly fine. Third is that there are a few particles that we should understand the basic structure of. For example, ammonium. Again, I'm restricting ourselves to just O levels and IGCSE over here. Ammonium changes to ammonia and a hydrogen ion. Water changes to hydrogen ion and hydroxide ion. Now, that does not mean that water is always this, but it may. And carbonate changes to carbon dioxide and oxide ion. So if you understand these ions, then you understand how to work with it. For example, if I have ammonium nitrate, then I can think of it as ammonia and HNO3, because this H and that nitrate ion, they work together, and I'm able to figure out the balancing from over there. So if you understand how ammonia works or ammonium works, then you will obviously understand the balancing. It won't be that difficult for you. And then one more method that I would suggest is, if you're in doubt, if you have like odd numbers on one side, even numbers on the other side, then use the LCM method. Now, what is LCM method? For example, I have three atoms of one thing on one side. Let's say I have three atoms on one side and two atoms on the other side. And there's the arrow in the middle, and there's a lot of other things. What I would suggest is take the LCM of 3 and 2. And that is 3 and 2, the LCM is 6. So make 6 on both sides. What do I multiply 3 with to get 6? 2. And what do I multiply 2 with to get 6? 3. And that will usually help you in balancing this thing. Similarly, if I have something is 5 on this side and on this side something is 3, how do I balance it? Just figure out the LCM. 3 and 5, 15. Multiply this with 3, multiply this with 5, and it will help you in balancing them. And lastly, another method that I've picked up over the years is that if you ever have ratios that are in fractions, if you have fractions, then let the balancing factor be in fractions. And good news for O levels guys, for the last 2 or 3 years, Cambridge has started to accept fractions in their final answer. So you can write fractions in your exams, but you don't have to. If you get fractions and they make you uneasy for some reason, then multiply or double the whole equation. So if fraction, like if it is fraction of half, then double the whole equation. Or if the fraction is of 4, then multiply the whole equation by 4. So basically, whenever you have a fraction, it's perfectly fine to have a fraction, but if you want to get rid of a fraction, just multiply it all by 4. Now, while I have written all these 5 points, the best way to really understand this is to put it to a test. So let's try to balance a few equations, and then we will fully understand how this thing really works. All right, so let's suppose I have this, I've downloaded this worksheet from aboutchemistry.com. It's a really useful website, and I would suggest that you go there for some worksheets. In fact, for the teachers in here, I would suggest get your worksheets from here. They're very well made. All right, so let's see how we can balance this out. Again, what are we working with? We are working with ions here. I have iron, I have sulfuric acid that is going to form sulfate ion. So let me underline them. This is iron, this is hydrogen, this is sulfate. So hydrogen ion, sulfate ion. This is iron ion, sulfate ion, hydrogen ion. Hydrogen atom, of course, making hydrogen molecule. All right, so let's begin. I'm going to do any other particle, then hydrogen, then oxygen. So I have 2 iron on the right side. Now I'm starting with iron. You could have started with anything else. So I have 2 iron on the right side. I have 1 on the left side. So my ratio is 2/1. So I'll just write 2. Okay, iron is balanced. I have 3 sulfate on the right side. This number 3 tells me that I have 3 sulfate. And on the left side, I have 1 sulfate. Now, a common mistake is that students assume that this 4 is basically telling me how many sulfates I have, but that's not the case. The 4 is basically part of sulfate. This is a molecular ion that we have worked with. So watch the previous lesson if you want to know what molecular ions are. So this 4 is actually part of this, which means I technically just have 1 sulfate ion. This whole thing, SO4 is 1 sulfate. So I'll multiply. I have 3 sulfate over there, 1 here, 3/1 is 3. So I'll just multiply this by 3. And that means sulfate is also balanced. What about hydrogen? Now I have 3 times 2, 6 hydrogen on the left side and 2 on the right side. So 6 divided by 2 is 3. So I just put 3 here and my equation is balanced. All right, so that's my first equation. Of course, as you move along, you will understand and you will understand better techniques. So it will be much easier for you over time. But I would suggest once in your O-level program, make sure that you practice this worksheet. This has like over 100 different equations, each with its own challenges. So the more you practice, the more you get better at it. And once you get better at it, it's perfectly fine for you. All right, let's look at the second one. Now, here's the thing. Before we do that, another important thing to do would be to understand what equation represents what kind of reaction. So for example, in the first one, what's happening? Let's try to make sense of that. Iron is displacing hydrogen. Because over here, sulfate is with hydrogen, but over there, after the reaction, sulfate is with iron. So iron has displaced hydrogen. This is telling me that iron is a more reactive substance than hydrogen ion. Also, if I want to know in terms of oxidation and reduction, then iron has been oxidized. So I can say that iron is a better reducing agent than hydrogen in this case, which is why it's able to displace it. Similarly, the next question represents oxidation or combustion, depending on whether you have a flame or not. If you have a flame, this reaction, the second equation, would be combustion. And if you don't have a flame, it will be oxidation. So, all right, so let's see. I have 2 carbons on the left side, just 1 on the right side. So 2/1, that is 2. I have 6 hydrogen on the left side, just 2 on the right side. So 6/2, that is 3. Now, how many oxygen I have? On the left side, of course, I just have 2 oxygen. But on the right side, this is 3 times 1, that is 3 here. And 2 times 2, that is 4 there. So 4 plus 3, that is 7. So I have 7 oxygen. On the left side, I have 2 oxygen. So the ratio comes out to be 7/2. And you're good to go. You can submit this in your O-levels exam and it will be marked correctly. But let's suppose you don't like fractions for some reason. Then what I would suggest over here is double the whole thing. All right, so let's do that. This number is 1, so it will become 2. This number is 7/2. So what happens if I multiply by 2? The 2 cancels out. So I'm left with just 7. Similarly, this number is 3, so it becomes 6. And this number is 2, it becomes 4. And there you go. We're done. All right, moving on. Now, again, let me underline what particles I'm working with. I'm working with potassium here, hydroxide here, hydrogen here, phosphate here, potassium here, phosphate here, and this is water. Now I've told you that water is basically H and OH. H and OH together, they make water. So let's just think of water as that. It doesn't hurt to think of it like that. Of course, you can balance otherwise, but this is something that I prefer to do. All right, so let's start with potassium. On the right side, I have 3 potassium. On the left side, 1, so 3 is my number. On the right side, I have 1 phosphate. On the left side, I have 1 phosphate. It's balanced. Notice that I did not balance phosphorus or oxygen. I balanced phosphate. Similarly, on the left side, I have 3 hydrogen. Now, you might be surprised because you also have hydroxide. So I'm not considering that as hydroxide as O and H. I'm thinking of that as just OH, hydroxide together, a molecular ion. So I have 3 hydrogen here, and how many on the right side? If you look over here, that is 1 because I have hydroxide as well. So I'm going to write 3 there, 1 here, that is 3. And the interesting part now is that OH is automatically balanced. I have 3 OH on the left side, 3 on the right side. It is perfectly balanced and my equation is done. All right. Now this one is basically a reaction of hydrogen ion and hydroxide ion, which we call a neutralization reaction. So far we have seen displacement, combustion, neutralization. All right, moving on. This one, tin 4 oxide and hydrogen react, and again this is displacement reaction, because you notice that oxygen is with tin over there on the left side, and over on the right side is with hydrogen. So it shows that hydrogen is more reactive than tin. Not just that, it is also tin losing oxygen. If you look at tin is losing oxygen. So because we know reduction and oxidation are related by definition of oxygen, oxidation is loss of electron, but it's also gain of oxygen. Over here, tin has lost oxygen, so tin is reduced. So that means hydrogen is a very good reducing agent compared to tin. So that's what happens here. I have tin balanced out. I have hydrogen balanced out, but not oxygen. So I have 2 oxygen on the left, 1 on the right. So it goes 2 here. And now what happens? I have mismanaged the number of hydrogen. It's not in balance anymore. So how many hydrogen do I have? I have 4 on the right side, 2 on the left side. That gives me 4 over 2, just 2. So I'm done. This work is done. So this is reduction using hydrogen. We use it when we are extracting different metals, especially when the metal is less reactive than hydrogen. Where do we get hydrogen from? We get it from cracking of hydrocarbons, but cracking of petroleum. Cracking is basically when you take a big molecule and you break it down into smaller molecules using heat without oxygen, because in presence of oxygen, they'll just burn. Next question is again ammonia reacting with oxygen. So we'll say this is oxidation. So ammonia is reacting with oxygen and oxidizing to form NO. There's something interesting about NO. NO is actually a catalyst in the whole process that depletes ozone. You know, ozone is this layer at the upper atmosphere that keeps harmful rays of sun outside. So nitrogen monoxide, which is formed in car engines, if you don't have catalytic converter, it will just go out through the exhaust and go into the atmosphere. So this is a catalyst. This speeds up the reaction that ultimately depletes ozone. All right, so let me see. Nitrogen, hydrogen, oxygen. Nitrogen, oxygen, hydrogen, and oxygen. So I have nitrogen balanced out, 3 hydrogen on the left, 2 on the right. I would like to use a fraction here. So 3 over 2, there you go. It's perfectly fine to use a fraction like that. But if you don't like it, double the whole thing. So you can double the whole thing if you want. But here's the thing. Let's just hold on and see what happens. Now I have nitrogen balanced out, hydrogen balanced out, but not oxygen. So I have 2 oxygen on the left side. How many on the right side? And this might be a little tricky. 1 nitrogen oxygen here and 3 by 2 oxygen here. 3 by 2 is 1.5. In other words, I have 1 plus 1.5, 2.5 oxygen. Wait a minute, 2.5 on the right side, 2 on the left side. What is that number? That is 2.5 over 2. If I try to make it into a fraction, this fraction comes out to be 5 by 4. 3 by 2 on the right side, 5 by 4 on the left side. What's happening? Well, what's the LCM of 2 and 4? 4. Multiply the whole thing by 4. So this is 1 times 4, 4. This is 5 by 4 times 4, just 5. This is 1 by 4, so that is 4. And this is 3 by 2 times 4, so that comes out to be 6. Because 1.5 times 4 is 6. Thank you so much, Abdullah Huda. Yeah, this mic is really good. This is amazing. Thank you so much. Yeah, पता नहीं कैसे हो जाती हैं दुनिया में ऐसी चीज़ें. Alright, so we have this fraction that we have balanced out. And again, this is oxidation. So based on this, I would suggest you try to work these things out, and you will notice that these 5 rules that I've just given you, they will work out for you, these 5 rules. And if you're able to make sense of them, and of course, this is not a hard and fast rule. All of these, I have made them up myself as I've studied chemistry and as I've taught chemistry. But if you find a better rule, do share with me and let me know what you come up with. So write that on a comment. I will be sharing this worksheet with you. Make sure that you take out some time. You can do it in a week, maybe do 10 exercises, maybe do 10 equations a day and you'll be fine. Or you could do like 20 if you're ambitious. But try to work this worksheet out, and if you're able to do it, there is absolutely no equation that O-levels or IGCSE can throw at you that you will have trouble with. Alright, so that's it for today. Thank you so much for joining in, and I'll be available if you have any questions. Make sure that if you find these lessons useful, ask your friends to join in, subscribe and share with them. I'll see you in the next class. We will do periodic table now. So stay tuned. Allah Hafiz.